Hello everyone and welcome. This is Aurora with the Central Coast Astronomical Society, and we were really excited to be having our special guest, Dr. Jessie Christiansen, talking to us tonight about On the Road to a Billion Planets. Now, we haven't actually started yet. It's actually going to start in about 12 minutes, but I want to make sure that all of our videos and our audios are working, so I want to, we're just going to do some technical gymnastics, so you can watch that if you'd like, but otherwise we're going to start at the top of the hour, and I will see you back here really soon. Hello, this is Aurora with the Central Coast Astronomical Society, and we are just doing some audio checks. I will be back shortly. Hello, this is Aurora with the Central Coast Astronomical Society. We are doing our sound and our video checks to make sure that the lip flap is matching what that you hear. So we'll be back shortly. We're just blipping in and out, doing some more technical gymnastics, and I will see you in a minute. Hello, this is Aurora with the Central Coast Astronomical Society. We are going to be looking how to talk with Dr. Jessie Christiansen shortly. We're just doing some audio checks. We've got some problems with the microphone, so we're just working those out. I will be back in just a few minutes. Hi there, this is Aurora with the Central Coast Astronomical Society. We're just working on our mic levels and our videos and getting everything ready. I will see you guys in about 7 minutes. Hey there, this is Aurora with the Central Coast Astronomical Society, and we are doing just some sound checks and video checks. You see the elbow of my technician here. This is Al, my husband. So we're going to be starting really soon, and I just wanted to check and see how the sound was doing. You can let me know in the chat box how it's sounding. It looks like we're just about got everything ready to go, and I will see you guys in just about 4 minutes. Hello everyone and welcome. This is Aurora with the Central Coast Astronomical Society. I'm so excited that you're going to be joining us tonight. Now, I know I'm here a few minutes early. That's to make sure you've got your volume set right, that if you have any questions about connecting, we are here to help you to answer those as well. We actually have a full night planned for us, for you, and I'm going to introduce you to a couple of really cool people, and I know you're going to like them. So before we get started, I just want to make sure that you have with you a pencil and a piece of paper so you could write down any notes like during this presentation tonight. So if you hear us say something, you are wanting to participate in the next stargazing, or our guest speaker says something and you're like, oh, I want to, so you have a place to write your notes down. Go ahead and get that now. This class will be recorded, or this session will be recorded, and it'll be posted on the Central Coast Astronomy website. Now you may notice that there's like a couple of links down here. So last time I got inundated with a ton of different questions from all different areas. And so we're trying to consolidate the way that you ask questions so we don't miss anybody. The best way to ask questions is through the chat box. Now you should see it underneath the player. If it's full screen, you can hit escape or minimize to kind of make it, or not minimize, but you know, just to make it smaller so the chat box will pop up. And if you still don't see it, but you still want to ask a question, or you want to do it privately, we now have 2 different ways to do that. You can text this number. Don't call it. There's nobody there. But it is accepting texts, and so you're going to text that number down there. And the number, in case it's a little fuzzy on your screen, it's 805-242-6415. So 805-242-6415. So we've set that up so you can go ahead and text your questions anytime during our presentation tonight, and you'll be able to get that question submitted so our astronomers can answer that for you. You can also email your questions to questions@centralcoastastronomy.org. So questions@centralcoastastronomy.org. Okay, so I'm so excited that you're joining me. Can you guys go ahead and just introduce yourselves, put your fingers on the keyboards, and just say hello and hi and welcome. Let me know how the volume is sounding. Let me know about something that you're especially interested in learning about tonight. And I'm going to do one of my final checks, and then I will be right back. Hello everyone, and welcome to the Central Coast Astronomical Society's special presentation for Thursday night. I am so excited you're joining us. I am the president of the Central Coast Astronomy. My name is Aurora Lipper, and I have been doing astronomy probably for about 15 years. My husband gave me my first telescope, took it completely apart, hid it in different appliances around the house, and I had to put it all back together. So that was my introduction to astronomy. Now, we are based in San Luis Obispo, which is halfway between San Francisco and Los Angeles. From those of you who are joining us from further away from the local area, we want to extend a special welcome to you. Now, with me tonight, we also have one of my friends here, Brian Cox. He's going to be helping. Let me introduce him. Brian, you there? No, you're not there. There you are. Now we can hear you. Okay, go ahead.
Yes.
I want to introduce Brian. He is actually from the Riverside Astronomical Society, but he is helping us out with a lot of the technical stuff on our end to help bring this to you. Do you want to say hello, introduce yourself, Brian?
Yes. Hi, Aurora. Thank you. My name is Brian Cox, and hello to everyone watching this live or as a recording. And I am also a member of this astronomy club to Central Coast Astronomical. And, you know, Aurora, I thought I'd take a moment. This be a good time to share about our Facebook page and about the new member gallery that we have? Okay.
I have no sound. Yes, absolutely. Why don't you go ahead and do that?
Great, I'm going to do that. So we have a new, as I just started to mention, we have a new Facebook gallery for all of our members. And so what you can do as any participant on Facebook, you can actually go and watch. I'm going to get the right screen up here. Let's try this one. All right. Okay. Live television. Great. On our Facebook page, if you take a look over on the left-hand side, we have a section called Group. And when you look at groups, we have one here called Central Coast Astronomical Society Member Galleries. Now, anyone can watch the galleries that we have here and take a look through all the different pictures. We still have members who are working on posting everything. If you're a member of the Astronomy Club, you can click Join, and then that gives you the ability to post images. But we invite all of you to go take a look, not only at our Facebook page, be sure to like that, but then you can follow or take a look at our member galleries by clicking on photos, and you can see all the different astronomy photos. One of our members named David, he just posted some, and I have a few up here under the album section too. So thanks, Aurora. I'll pass it back to you.
Awesome. Thank you so much. All right, so if this is your first time joining us, I want to extend a special welcome to you. We are doing our presentations online like many astronomy clubs. However, we've been doing this for a few years, so it's really fun to be able to interact with the audience. And the way we do that is by having you submit your questions. The best and fastest way is to put them straight through the chat. You guys can say hi to each other. I've already seen Glenn Elliott. Hi! Go ahead and use the chat box as much as you like. And for tonight, Brian is going to help answer a lot of those questions that are in there. And then also, in addition to the chat box, I've actually posted here, I'm going to make this go away shortly, but if you have questions by email, go ahead and submit your question to questions at centralcoastastronomy.org, or you can text this number. That text will get turned into a message that goes straight to Brian. And so if you want to ask a question privately, but you'd like it answered by the astronomers tonight, then that's a way to do it as well. Okay, so we are going to go ahead and get started. I have a couple of quick announcements before we bring on our main person for tonight. So I'm really excited to introduce you to her. She is amazing. But before I do, I want just to make sure that you know about some of the things that are coming up with the Central Coast Astronomy Society. And some of these are free, open to the public, and some of them are just for members only. So let me show you those right now. On my screen over here, you'll see our website, centralcoastastronomy.org, O-R-G. And this is our presentation we're going to be doing tonight. Also coming up in 2 days is a free webinar for the Society of Astronomical Sciences. This was submitted by CCIS member Tom Smith. All the information you need is here. You can click on that if you're interested in presentations on a wide variety of topics like imaging basics, photometry, spectroscopy, instrumentation, all of that. And so members of CCIS can sign up for that a webinar for free, and the details are on this page. Our next star party is on June 13th. Mark your calendar, 7 p.m. We are going to be doing that on this website. We'll be doing that as we have been doing it for the past couple of months. Kent Wallace and myself will be taking you on a tour of the night sky. Super fun. We're actually going to provide you with a handout ahead of time, so you'll know what we're going to talk about. So as Kent and I go through it, you can make notes and mark things down. So that'll be yours to take home, in addition to the sky maps that we will suggest that you download. So that's available as well. Okay, and then there are other articles in here if you want to pick the right eyepiece and getting started with astrophotography and so forth. That's all in here as well, and you can look at other events. We have a calendar that you can peruse as well. Okay, are you guys ready for our main speaker tonight? Okay, before we bring her out, well, actually I have to call her, so give me a minute to do that. But before I do that, I want to ask you a question. I want you to answer the question for me if you could. So our guest speaker is going to be speaking about, well, first I should introduce her properly. Here, let me start to ping her so she can come up. Give me just a second. Okay. Okay, so in just a minute, I'm going to bring her up. She is a NASA exoplanet science. She works at the NASA Exoplanet Science Institute at Caltech, where she searches for and characterizes and catalogs the planets that are orbiting around other stars. So if you think about it, all those stars that are out there, they may or may not have planets around them. Some do, some don't. We don't know what the percentages are like necessarily. We're learning that every day. So one of the questions I would like to hear from you before she starts her presentation are, what are some of the questions that you would have for her? So if you can think about a question now and type it in, go ahead and start that now. And then as she's doing her presentation, you may find that she actually answers that question automatically for you. So go ahead and think about it now. What would you want to ask a real astronomer if you could? One that does their work by trying to find planets around different stars. I mean, how cool is that, right? That's astronomy at its core. So what would you like, what would you like to ask her? So go ahead and type that in, and while you're typing that in, I'm gonna go ahead and give her a ring. Okay, and make sure you do write that number down that's on the screen. She will, we will be taking this off during her presentation. So if you have questions, remember the email is questions@centralcoastastronomy.org. You can also text 805-242-6415. If you prefer to do that and not have it on chat, that's totally fine. It's we're all set up to do that as well. Okay, so I want to introduce somebody amazing to you, Dr. Jessie Christiansen. She is an astrophysicist with the NASA Exoplanet Science Institute at Caltech. She doesn't probably realize she's on, but she is, and everybody can see her beautiful smiling face. And in 2018, she was awarded the NASA Exceptional Engineering Achievements Medal for her role in the successful NASA Kepler mission, which discovered thousands of exoplanets. And she's going to probably tell us a lot about that today. She's working now. Well, actually, I'm just going to have her talk because coming from her, it's going to be even better. How's it going?
Hi, can you hear me?
Yes, we can hear you fine.
Okay.
Are you ready?
Yes, I had a little tiny computer kerfuffle just like 3 minutes ago, just in time to make me really flustered right before this.
No problem. No problem. I know we have a lot of people that are so excited for your presentation tonight, so I'm going to let you take it away.
Great. Let me share my screen.
Sure. Take your time.
Window, this one. Start sharing. All right. Can you see that slide?
Yes, I can see your slides. Yep, and it's just the one slide that I see now.
Brilliant. Okay. Hi, everybody. As Aurora said, my name is Jessie Christiansen. Thank you so much for having me tonight. I know this is not the Amateur Astronomical Society meeting you usually have, but, you know, one good thing about it is it lets me talk to people that I wouldn't normally get to talk to. I've talked to a lot of the local astronomy clubs in LA, so this is really quite wonderful that I get to reach out and talk to more people. So thank you for having me, and thank you to everybody who's dialed in tonight. I know it's bath time and bedtime for a lot of people, so I'm excited to spend this time with you. So tonight I wanted to talk about exoplanets, and I'll go into that a little bit more detail. I've called the talk On the Road to a Billion Planets, which seems very ambitious, but I want to talk to you about our plans to get from where we are to that, with the slight caveat that almost everything we found so far will kill us, which, you know, not ideal, but I'll talk about our hunt for things that won't. Okay, so let's start with what's an exoplanet. This is our solar system, not to scale. We have one star in the middle of our solar system, the sun. We have 8 planets. I know, I'm very sorry about Pluto. This was before I came of professional astronomical voting age, so I didn't actually get a say, but we have 8 planets in our solar system. We also have dwarf planets, which is basically the bucket that we invented to put Pluto and objects like Pluto into. One of the reasons Pluto got demoted was because it didn't actually look like the rest of our planets in our solar system, and it did look a bunch like all of these new things that we're finding further out. So we decided that they were really a new class of objects, of which Pluto was the first, dwarf planets. We also have minor planets in our solar system, which is basically everything else that's bigger than a grain of sand that we've been able to detect, which includes the dwarf planets. It also includes asteroids, Trojans, centaurs. These are different kinds of asteroids in different orbits around the solar system. Kuiper belt objects. So these were the things further out from Neptune that Pluto ended up being, you know, one of the largest of. Trans-Neptunian objects. If you add up everything else we found in the solar system besides the sun and the 8 planets, there's 710,000 things that we've catalogued. So, you know, although space is very empty, it's also got a lot of stuff in it. But what are exoplanets? Exoplanets are planets around other stars. So our sun is one of 100 billion stars in the Milky Way galaxy. So for thousands of years, since the Greek philosophers, so 2,500 years ago, for thousands of years, people have looked at the stars in the sky and wondered, first, what they were, and then, once they realized they were stars, if they had planets around them too. So the Greek philosophers actually talked about Earth and whether Earth was rare, like there's just one Earth and no other kinds of Earth, or whether there were many Earths. And Plato and Aristotle actually argued that Earth was unique, that there would never be anything else like the Earth. So that was 2,500 years ago. Let's fast forward a little bit. Now we're in the 16th century. We're in the Renaissance. So the Renaissance was an amazing time for art and science and literature in Europe. Many other cultures around the world had already had their Renaissances, so Europe took a little while to get there. But I wanted to quote this person. So Giordano Bruno was an Italian mathematician and philosopher, and he said this: "There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our solar system." This was before they knew about Neptune and then Pluto and then not Pluto again. So at this point, there were 7 planets that they knew of. Now, this is really interesting. So he's basically saying, look, all of these stars, they're just like the sun. Our sun has planets. Why wouldn't these stars also have planets? Which was a fair point. Unfortunately, he said this at a time when it was basically heretical. It was against the Roman Catholic Church's teachings to say something like this. He also said a bunch of other pretty stupid stuff when he shouldn't have. And he was actually burned at the stake in 1600 for saying, amongst other things, that there were exoplanets. So thankfully for me, as an exoplanet hunter, I don't have that same risk in my day-to-day life. But I appreciate Giordano Bruno for paving the way for us. Okay, let's fast forward now. We're in the 20th century. So now we have a pretty good idea of what stars are, and we know that a lot of them are like the sun. an astronomer, Otto Struve, actually comes up with a way. He's like, how could we detect potential planets around these stars? Because, the problem is that stars are really, really, really big and planets are really, really small. Even the biggest planets, so Jupiter, for instance, in our solar system, is only 1% the mass of the sun. And the rest of the planets don't even add up to 1% together. So planets are really tiny, even the big ones, compared to stars. So we already knew that they were hard to find. Otto Struve comes up with this technique. So we already knew about binary stars. Binary stars is when there's two stars that are orbiting each other. They've gotten trapped in an orbit together. And in fact, most stars are in binaries or triples or hierarchical triples. Our sun's in the minority, just being on its own, being lonely. So we knew about binary stars that orbited each other with just a few days. Every few days they would go around each other. And we could see this because we could see the velocity of those stars. We have a way of measuring how fast a star is moving. And we could see that sometimes they were going towards us and sometimes going away, sometimes towards, sometimes away, as if they were orbiting each other. And Otto Struve was like, okay, what if we took away one of those stars and instead put a giant planet there? The giant planet would be much smaller than the star, but it might be big enough that you'd be able to see the velocity change in the star. This is called the radial velocity technique. And at the time, all of the other astronomers were like, Otto, that's crazy. I mean, how could you make a giant planet like Jupiter and have it orbit only a few days from its star? Like, there's no way to form a giant planet right there. The gas that it would have formed out of would have been just sucked into the star to start with. But how do you start something way out where Jupiter is and then migrate it all the way in so that it stops just near the star? It doesn't go all the way and crash into the star, it just stops. So they were basically like, that's a fun idea, but that's basically never going to happen. Okay, let's fast forward to only 25 years ago now. 25 years ago, the very first planet orbiting a star like our sun was found. So we'd known about this idea for thousands of years, but it took a long time for our technology to catch up with our ideas. We had this imagination, we had these ideas, but we had to build the right instruments. And one of the things we had to build was digital cameras. So like the sort of thing that you're carrying around in your iPhone every day. We needed to invent those before we could find these planets. So in 1995, the first planet gets found. And it was found using the radial velocity method. And it was a hot Jupiter. It was a Jupiter-sized planet that was orbiting its star every few days. So Otto Struve was completely vindicated with this like crazy idea that he had come up with that everyone had ignored. All right, so that was from 2,500 years ago to 25 years ago. That's where we're at now. All right, since then, since we've realized how to do this and made our instruments better and better, the number of known planets has been increasing exponentially. And now in the time of the pandemic, you've all seen exponential curves. So you know what this is. It's something that just keeps rising and rising and rising. It's accelerating the rate of discovery. And in fact, if you plot this another way, if you plot it in a linear plot, which if you're following the pandemic curves, you've probably seen that too, what you see is that the number of known exoplanets is doubling about every 2 years. Which is actually similar to Moore's law, which, if you've heard of that, is this computing adage that that processing speeds of computers double about every 2 years. So it seems like exoplanets are doubling about every 2 years too, which is really exciting because the more planets you have, the more you know. So what do we know about? Oh wait, I can see Aurora is covering my circle that I put. All right, so the prediction, if we keep rising exponentially, is that we'll hit 1 million planets in 2034, which is only 14 years from now, and 1 billion planets in 2057. So that comes from that's where the title of the talk comes from, this prediction that we will hit 1 billion known exoplanets in the next 30 or 40 years. So how are we going to get there? Okay, get back here. And I've called this Mamajeck's law after Eric Mamajeck, who was the astronomer who came up with it. So if I'm trying to make it stick, so if you could just use it in everyday conversation, find some time tomorrow to just throw Mamajeck's law in, I would really appreciate that because I would like to make that stick. Okay, so this is the known planets in 2010. And just to make these axes a little bit easier to read, I'm just going to change this one. So the one on the bottom, I don't know if you can see my cursor. So this is the period of the planet. So this is in days. So 100 days, 200 days, 300 days. So this is Earth. And these are our inner solar system planets, Mercury, Venus, Earth, and Mars. On this axis here is the size of the planet relative to the size of Earth. So 1 Earth radius is here. And Jupiter is up here at like 11 Earth radii. So just to make these axes a little bit easier, this one is, as you go to the right, you get further away from the star. And this one is, as you go up, you get bigger. Now you can see in 2010, before 2010, mostly what we knew about were these hot Jupiters that Otto Struve had predicted. So these are Jupiter-sized gas giants, huge planets that are orbiting their star in just a few days. So this is 1 day, 2 day, 3 day, 4 day. So these are heated up to incredible amounts. These are thousands of degrees, which is why we call them hot Jupiters, because we don't have any imagination. We just, they are Jupiters that got heated up. But you can see there's this big gap in knowledge between what we knew before 2010 and what our solar system looked like. Our solar system doesn't have any hot Jupiters inside the orbit of Mercury. This is what we know as of last year. And you can see we've really filled, in the last decade, we have super filled in this space in here. Now we've got all of these things that are the size of Earth, things that are the size of Neptune, all of these things in between. We've filled out this space between 1 day and 100 days. So we have these populations that are appearing. We've got all these multi-planet systems, systems with almost as many planets as our solar system. You can see that we haven't quite got here yet, and I'll talk a little bit about why that is. So how did this happen? How did we have this huge explosion in the number of exoplanets? It was because of the Kepler mission. As Aurora nicely set up in her intro, I worked on the Kepler mission and still work on the data from the Kepler mission for about a decade. This was NASA's Planet Hunter, its first proper dedicated planet hunter. It was launched in 2009. It's a 1 meter optical telescope. So just, in the light that your eyes can see, that's optical light, visible light. That's what the telescope's looking with. And it stared at one patch of sky, a 10 degree by 10 degree patch of sky in the constellation Cygnus for 4 years. And it just stared, and it just stared, and it just stared. Frankly, it was pretty boring, the day-to-day operations of the spacecraft. I was often the duty scientist on the spacecraft, meaning babysitting it, essentially. It was very well behaved. It just sat there and stared at this patch of sky for 4 years. Occasionally, it would do something frightening, like once a year, it would just go into safe mode. Safe mode is not actually good, I will tell you that. It sounds good, right? Like the spacecraft's in safe mode, and you're like, okay, that's better than dangerous mode. But actually, safe mode is bad. That means something went wrong, and the spacecraft is like trying to protect itself. So anyway, diversion about the Kepler mission. So there's there's a field of view. So when you go outside, and in summer, you look up at night, there's Cygnus. This is the patch of field. We know of, thousands of planets in this patch of sky now. Okay. Yep, there we go. All right, so how do we find the planets? So we don't actually use the radial velocity method. We stare at this patch of sky, which had 200,000 stars in it, and we just stare at it, and we stare at it, and we stare at it, and we stare at it. We observe these stars over and over and over again, and we're just measuring how bright they are. Why do we want to know how bright they are? Well, this is an animation of 7 rocky planets going around a red dwarf called TRAPPIST-1. Now, normally those tiny rocky planets would be so small, you'd have no way of seeing them with radial velocity and no way of seeing them at all, except if you're lucky and the planets are lined up just right. So now you see the animation has switched so that we're side on to the planetary system. And every time a planet goes in front of the star, it blocks some of the light. So on the bottom, what you're seeing is the actual data from the Spitzer telescope, which is another NASA telescope that was used to follow up these planets. And it's just measuring the brightness of the star over and over. And occasionally you see these parts where it goes up. That's a flare. The star, got a bit excited and burped and a flare came out. But mostly what you're seeing are these dips. Every time a planet goes in front, let's follow this one, boop. Every time a planet goes in front, it blocks some of the light. And the total amount of light, the brightness of the star goes down. So this really gives us a lot of information. So the distance between the dips tells you the period of the planet. That's how long it took the planet to go around. So this B planet is going around basically every day and a half. This is a very hot little rock. The size of the dip, how deep this dip is, depends on the size of the planet. So big planets will block a lot of light, and then little planets will block a little bit of light. So transits actually give you the period and the size of the planet. So that's pretty nifty. 2 pieces of information for the price of 1. All right. The goal of Kepler, the main reason that NASA spent all this money to put up this spacecraft, was to find out how common planets like the Earth are. This is answering one of the questions that humanity's had for a long time, since 2,500 years at least. How common are planets like the Earth? And you can see from the planets that we observed, did we find any planets like the Earth? We did not. And partly that was because we made a mistake. When the scientists were designing the Kepler mission, when they were coming up with the plans for the Kepler mission, they had to guess how noisy stars were that were like the sun. So when I say noisy, remember that light curve data that I showed, all those fuzzy white blobs. That fuzz is because the star isn't just a single point of light on the sky. You've seen these beautiful high-resolution images of our sun. The surface is boiling and cells are coming up and going down, and there are sunspots and there are flares. Stars are actually noisy. And it turns out that stars are noisier than we thought. No one had ever measured stars with this level of precision before that we did with Kepler. So we assumed that our sun was normal, which is usually a safe assumption to make. There's no reason to think our sun is special. But it turns out that our sun is actually quiet. Most stars are noisier than the sun. And when things are noisier, those dips that you saw, if that fuzz in the light curve, if the noise gets too big, then you can't see the dips anymore because the dips are within the noise. So it actually turns out that these small planets, the Mercury, Venus, Earths, and Mars, they're just too small for our telescope to see. We really needed either a bigger telescope or to observe for longer. So we still don't know. We can extrapolate. So that means we can guess from here, like seeing that these numbers are increasing as we go this way before the sensitivity of the telescope drops off. And we can guess from here, like you can see that this is kind of getting higher and higher before it gets to here. So extrapolating is dangerous because we don't know that there isn't some interesting physics or disk physics that happens in here that means that whatever the number is here can't just be extrapolated from these numbers here. But that's what we do. And if we extrapolate, which scientists do, we think that Earths are quite common. This absence here is because we couldn't find them, but these planets tell us that there must be heaps of planets out here. So we actually think that somewhere between 20 and 50%, so nearly half of stars like the sun have planets like the Earth. And by planets like the Earth, I mean rocky planets in the right temperature for liquid water to be on the surface. So that's really exciting, 20 to 50% of stars like the sun. Our galaxy has tens of millions of stars like the sun, which means tens of millions of planets like the Earth. And if you're thinking about, the possibility of life out there, if you believe that Earth's real estate is the most habitable real estate, which it's hard to say because we only have a sample size of 1, that's a lot of habitable real estate in our galaxy. That's really exciting. I wish we could constrain this number better. When I say we think it's between 20 and 50%, it could be 1% or it could be 300%. Those are some of the error bars. So we haven't nailed it down yet. Okay, what did we find though? This is Kepler 186. No, this is Kepler 452. Got to remember from the image. This is Kepler 452. This is a planet which is about 1.5 times the size of the sun. 1.5 times the size of the Earth. It's orbiting a star like our sun, and it's the right temperature for liquid water. So the size makes us a little bit worried because once you start getting too much bigger than the Earth, you start to accrete a lot of gas, and you might end up something more like a Uranus or a Neptune. Or if you get too big, you end up something like a Jupiter or Saturn. So 1.5 might be rocky. We think it's got about a 50-50 chance of being rocky. The problem with Kepler 452b is that it might not be there. The noise that we see in the light curve looks a lot like other noise that we see in other light curves that's caused by the spacecraft. The spacecraft is not just a little, perfectly behaving set of wheels and electronics. It's doing its own little personality quirks. So it might be real, but it might not be real. We haven't nailed it down yet. We're trying new ways to nail it down, but we don't know. So if it's real, it's the most Earth-like thing that we found so far because it's around a star like the sun, it's got the right temperature for liquid water, and it might be rocky. This is the most Earth-like thing we found if it's real. This is Kepler 186f. This is, now I'm going to change my mind again. It's still not Kepler 186f. I really need to label these. This is Proxima b. So Proxima is the closest star to our solar system. So this is Proxima, and here's Alpha Centauri A and B over here. There's actually a triple system. There's 3 stars. Alpha Centauri, the brightest star in the Centaurus constellation, is actually a double, Alpha Centauri A and B. And then there's a nearby small, cool red star, like TRAPPIST-1, the star that I showed you earlier, called Proxima Centauri. And it has a rocky planet in the habitable zone. So that's really exciting. It's definitely rocky. It's definitely in the habitable zone. The problem is the star that it's orbiting is one of these M dwarfs, one of these small, cool red stars. The reason that's a problem is the radiation that these M stars puts out look very different to the radiation that our sun puts out. And in particular, there's a lot of high energy X-ray and ultraviolet radiation that they put out many times higher than our sun. So, for those of you who live in California, UV radiation is the stuff that gives you sunburn when you go to the beach, can give you skin cancer. It's generally bad for life. If there's too much of it, we actually use UV light to sterilize things, like just to kill everything. So UV is bad. X-rays, also not great. That's the thing that they make you wear lead aprons before they give you. So we're a bit worried that these rocks that orbit M dwarfs might just get sterilized by all this radiation. They might not be able to support life. But the jury's still out. We don't know. Our sun, very early in its life, when the Earth was forming, also put out a lot of UV and X-ray radiation. Very young stars do this as well. You know, they go through this teenage emo phase where they're like, yeah, let's put out a lot of high energy radiation. They're like listening to the loud music. So we don't know. This might be habitable. It might be Earth-like. It might not. It's the second closest thing we have. So we've actually found 7 of these rocky planets around M dwarfs that are in the habitable zones. There's Proxima Centauri. There's a few that were found by Kepler. I really apologize just for the names. I just want to personally apologize to everybody listening to this. Astronomers have garbage names for planets. Like this is GJ667cc. Like that's nonsense. And I wish I could change it, and I can't. And then there's 3 of those rocky planets around the TRAPPIST system that I showed you, which are actually in the habitable zone of that star. So we have 7 rocks around M dwarfs, which may or may not be habitable. Fingers crossed that they are, because most of the stars in the galaxy are M dwarfs. So if these are habitable, then the habitable real estate in the galaxy goes up by 2 orders of magnitude. There's so much habitable real estate in the galaxy if rocky planets around M dwarfs are habitable. Fingers crossed. But what I want you to take away is that so far we have found nothing that is like the Earth. We believe that there are lots of things out there like the Earth, but we haven't found any yet. Okay, what did we find? Well, we found lots of hot Jupiters, which I talked about a little, and I'll show you a cool movie of. This is HD 189733. Again, I'm sorry, they just have such terrible names. So this is a hot Jupiter, so it's orbiting its star about every 2 days. And it's actually so close to its star that the star is ionizing the atmosphere and just buffeting the top of this atmosphere away. Like this planet is just losing mass because it's so close to its star. It's like, if you held up an ice cube to a hairdryer and just turned it on full blast, and the water drops are just like fluming away from the ice cube. So this is the sort of hellscape that hot Jupiters are. So when I say on the road to 1 billion killer planets, these are some of the ones that I mean, hot Jupiters. HD 189733 is in fact so hot that we've been able to measure the wind speed of the atmosphere, and we've been able to measure that there are silicates in the atmosphere. So that's glass or like sand. So basically, we know that on HD 189733, it's raining liquid glass sideways all the time. That's how hellish it is. That's how hot and awful it is. Very bad. So like there's like California, there's HD 189733, and then there's Arizona. Like that's how bad it is. Okay, so we found hot Jupiters. We also found lava worlds. Now this is I actually think that's a pretty cool name, lava worlds. So these are rocky planets. So we're down here at one times the size of the Earth, about Earth size. And this is 1 day. So these are planets that are orbiting their star in less than a day. These take hours to go around. So, if you were celebrating a birthday on one of these worlds, you'd be 10,000 years old by now. So these are rocky planets that are so close to their stars that the surface of the planets is melted. It's just liquid magma. These are just like blobs of magma floating around in space. So I have another cool image, another cool movie. So this is Kepler 10. So Kepler 10b, which was actually the first rocky planet that was, robustly confirmed to be rocky. And it was found by the Kepler mission. There were planets that had been found before, which people thought were rocky and had tentative measurements of rockiness, but this was the first one where we got, a very good measurement and we knew it was rocky. And so you can see the side of the planet that's facing the star is just so hot that it's melted. And this is an artist's impression. This is not real data. Again, we're just looking at the light curves and seeing these tiny little dips. But again, this cloud of stuff that we're going through, again, it's so close to the star that the star is just like ablating. It's like sandblasting the surface of this star, the surface of this planet away. So for people who get seasick, you might want to look away for like 10 seconds. We're going to go for a fly through the lava. So I was actually at MIT at a conference last year talking to a grad student, and she is in the lab making lava in her lab so that she can measure the way lava reflects light. so that we can guess, like, so with the big telescopes that we're building in the future, like the James Webb Space Telescope, and in the future, LUVOIR or HABEX, some of the big missions that NASA's studying right now, that we would be able to guess, like, what a spectrum of these things would look like. How would you be able to tell what kind of lava it was and what temperature it was and stuff? And I just thought, I'm just talking to a grad student who makes lava in a lab. I was like, that is so cool. Like, I'm so used to just sitting and getting data from a spacecraft that, you know, it's just on my computer screen. It's super boring. She's making lava in a lab. That's so cool. All right, so those are lava worlds. We did find a bunch of rocky planets that aren't necessarily lava worlds. We just don't think any of them are habitable yet. We found lots of Neptune-sized things, ocean worlds and ice giants. That's really exciting. The thing that we found the most of, though, are these things in between. So between the size of Earth and Neptune. So the reason that's interesting, we call them super Earths. The reason that's interesting, they're not where Superman came from. It just means big Earth. In our solar system, we have a gap. Well, we have a couple of gaps, but we have one big gap. So this is the size of Jupiter, and this is the size of Saturn, and here's Uranus and Neptune, about the same size. Now, Earth is down here. So Neptune is 4 times the size of Earth. So there's this big gap here in size. And then we have Venus and Mars and Mercury. But the most common kind of planet that we found, the thing that we've literally found the most of, is in between. It's a super Earth. The reason that's interesting is we don't know what they are. We don't know whether they're big rocks or whether they're small gas giants or ice giants. We don't know whether there's something we don't have in our solar system, like a water world. Some of them have the same density. It's just like a giant ball of water in space. So yeah, these are super exciting and super new and unexpected, and we still don't know what they are. So I'm going to talk a little bit at the end about the TESS mission, which is hopefully going to help us answer what these things are. But yay, surprises, because, you know, if everything was the same as the solar system, how boring would that be? Okay, speaking of things not being like the solar system, we found a bunch of other interesting stuff. So if I was there in person, I'd ask for a show of hands who recognizes what this is from, but I'm not. So I'm just going to assume that most of you do. This is from Star Wars. This is Luke's home world, Tatooine. And what you can see off in the distance, this is this iconic scene. He's looking at this sunset with 2 suns. Now, this was in the 70s. This is George Lucas in the 70s, guessing that there are planets around binary stars. And we found them. We actually found the equivalent of Tatooine. So we've found a bunch of systems now that have 2 stars around them, that have 2 planets in the middle. In all of these cases, it's 2 stars in the middle, and the planets are going around them. So the stars are so close together that the gravitational potential well looks like there could just be 1 star in the middle. Like the planets are far enough away from the 2 stars that they can just be treated like one big star. Otherwise, it's not stable. People ask about, like, can you get like cool figure 8 or horseshoe orbits? Like hypothetically, yes, but we haven't seen anything like that, and that would be very difficult to create and keep stable. So we found these things. George Lucas predicted these things like 40 years before we found them. And one of the things I wanted to point out is, look, he even got the colors right. There's a yellow star and a red star, and there's a yellow star and a red star. He didn't get the sizes right, but okay, he was like literally building these worlds out of thin air. I'm really impressed he got the colors right. So yes, we have found Tatooine-like planets. We've also found something that's really interesting. So our solar system seems like it's pretty spaced out compared to other solar systems we're finding. We have found many crowded systems. So this is TRAPPIST-1, which I showed before. I'll just start playing it again. This is TRAPPIST-1. So these 7 planets all orbit within a few weeks. So within like 20, 30 days. So the closest planet in our solar system, Mercury, is like 88 days. This is 7 planets well within the orbit of Mercury. Like, isn't that crazy? Just think how packed that system is. The reason they can stay like that is because they're usually in resonance with each other. They're locked in a resonance. So we have resonances in our solar system too, like the Galilean moons, Io and Callisto and Ganymede, I think, are the 3 of the 4 that are in a resonance. I'm going to have gotten that wrong. I rely on the amateurs to get me right on those kinds of things. And also Neptune and Pluto are in a resonance. So Aurora, one of the things I didn't think to check was, if I play sound on my computer, will you guys hear it, or is it just the screen?
It's just the screen.
Okay, so I'll talk you through this then. So this is a system that was actually found by citizen scientists. So that's people like you guys at home on your computers looking at data from the Kepler spacecraft. So this was a project I helped lead a few years ago. And this is a system called K2-138, again, I'm sorry for the names, it has 5 planets, and they're all in a chain of 3 to 2 resonances, just like Pluto and Neptune in our solar system. So that means for every 3 times this planet goes around, this one goes around twice. For every 3 times this one goes around, this one goes around twice. For every 3 times, et cetera, et cetera, et cetera, all the way out. Now, what you're not hearing is that means this system is musical, because a 3 to 2 resonance is the perfect 5th interval for any music students out there or instrument players. The perfect 5th interval is in the tonic chord. It's like one of the basic chords in Western music theory. So because you guys didn't get to listen to it, I encourage you to go to systemsounds.com and find this. This is a couple of people in Canada who have turned data into sounds, and they do it really well. And anyway, it kind of sounds like Twinkle Twinkle Little Star if you put it in a blender. And it's a musical system. It's very cool. And you too, you guys on the phone, this is my call to action. You guys on the computer can go and find your own planets. So we have a current citizen science project running using the TESS telescope, which I'll tell you more about, which is the sequel to Kepler, basically. Spoilers, Kepler actually broke in 2018. We weren't able to keep using it. Well, it broke earlier and then it ran out of fuel in 2018. But we do have a new project running, planethunters.org. And if you're all stuck at home in quarantine and not sure what to do, go find planets, and maybe yours will be turned into an awesome musical video, which I encourage you all to go watch. Okay, so I've mentioned TESS a few times now. Let's just talk through it. So yes, Kepler ran out of fuel in 2018. Thankfully, in 2018, we launched the NASA TESS mission. So where Kepler stared at that one patch of sky for 4 years with a 1 meter telescope, TESS is 4 10-centimeter telescopes, so smaller telescopes, but they have a much bigger field of view. So this is 24 degrees by 24 degrees. So Kepler fits in like a corner of one of these. And the 4 cameras do this big kind of orange slice on the sky. So in the first 2 years of its mission, TESS is going to look at almost the whole sky. So all the bright stars in the sky, TESS is going to hunt for planets around. And this was basically made possible because we found out that planets are really common and most stars have got planets. So we can just do this survey of all the bright stars in the sky and see which ones have planets. TESS is predicted to find 16,000 planets. So we're at about 4,000 now. So TESS is predicted to quintuple our currently known sample of planets. So yay, job security for me, since I work at the NASA Exoplanet Archive and my job is saving the data on all of these. All right, another upcoming NASA mission that I wanted to highlight. Let me check the time. Oh yeah, I'm doing good. The other upcoming NASA mission that I wanted to highlight is called WFIRST. So this is in the industry, we call it a beauty shot because it doesn't actually exist yet. So this is a pretty animation of a prediction of what WFIRST might look like. It's also very Star Warsy. So WFIRST is a new infrared telescope, a 2.4 meter telescope. It actually just got renamed just this week, I think. You know, time is meaningless in quarantine, but just this week it got renamed because WFIRST, as you can tell, is a terrible name. Now it's called the Nancy Grace Roman Telescope. Now, for people who aren't familiar with Nancy Roman, she's referred to as the mother of Hubble. She was a NASA administrator who pushed really, really, really hard for us to put telescopes in space. She was basically one of the driving forces behind getting Hubble launched. And when WFIRST launches in a few years' time, it's basically going to be the successor to Hubble in a lot of ways. So it's really fitting and really nice that we have this Roman telescope now. Also, I think it's the first space telescope named after a woman scientist. So that's exciting as a woman scientist. So yeah, we'll be calling it the Roman telescope from here on out, like the Hubble telescope. It'll be the Roman telescope. So I need to update my slide. Anyway, so WFIRST is an infrared telescope that will do two major things. One of them is look for dark energy. Now, that's a completely different talk that you need to get someone else to come and give you. But dark energy is basically the reason we think that everything in the universe is flying away from everything else in the universe really fast. The other thing it's going to do is look for exoplanets. So it's going to actually stare at the center of the Milky Way galaxy for 500 days. And it's going to use a technique called microlensing. So microlensing is kind of like black magic. It relies on Einstein's theory of relativity. Basically, if a star and a planet go in front of a background star, they act as a lens. They bend the light of the background star around them. So if you're just sitting there observing the background star, suddenly you see that star gets brighter as the star going in front of it magnifies the light. And if that star that goes in front has a planet around it, you see 2 magnifications. So Obviously, the best place to look for these microlensing events is where you have the densest background screen of stars. So that's why we're going to look at the center of the Milky Way, because that's where the most stars are. So it's predicted to find 100,000 planets. And the exciting thing is that WFIRST is sensitive to planets that are further out even than the planets we found so far. So this glob of planets here, now you're familiar with, I've shown you a few times, that's the Kepler results. So you have your hot Jupiters up here, you have your warm rocky planets here. So here's Mercury, Venus, Earth, and Mars again. That's that same 4 that we saw before. Here's Earth. So TESS, because it's doing the whole sky in 2 years, is not looking at long period planets. TESS is looking at very short period planets, basically just to identify which stars around us have planets, then we can study those stars in more detail. WFIRST is sensitive to cold planets, and that's really exciting because Kepler plus WFIRST covers the whole solar system. So in 10, 15 years' time, we'll have a much more complete census of the contents of the stars around us, what kinds of planets they have, and in what kinds of configurations. So these are really going to help us get towards this billion planets. And that's predicted to find 100,000 planets, which is super exciting again. And that keeps us on track. That keeps us on track to find 1 billion planets if we get those in the next decade or so, which is pretty cool. Okay. And the exciting thing, again, about WFIRST is they're just going to find these cold planets that hopefully not all of them will be deadly, because basically everything I've told you so far will kill you. So we're hoping that in the future we'll find much more amenable to life planets. And you can see the extrapolation here. We've kind of left it out here because we don't know the answer. We extrapolate the here and here. We think they're common, but we don't actually know yet. Okay. So this is another detection technique that I just want to touch on before we finish because it's so beautiful. This is called direct imaging, and it's actually, frankly, what it sounds like. We have some very clever instrumentation that blocks out the light from the star, and we look around the star to see what we can see. And sure enough, around this star, which is HR 8799, you can see 1 moving blob of light, 2 moving blobs of light, 3 moving blobs of light, and 4 moving blobs of light. You can actually see a ton of other little tiny blobs that come and go. Those are speckles. They're caused by the telescope, basically, in the air above the telescope. So this is all imaging that happens from the ground. But this is the first movie that we ever made of real planets. This is like light coming from this planet into your eyeballs. Into the CCD and then out of the computer monitor and into your eyeballs. But these are actual planets. This is a movie of planets moving around a star. You can see this covers, I think it's about 7 years. Yeah, this covers 7 years of these planets moving around. So these are very far out. These are like Uranus, Neptune style planets out here. But this is where we're at. In terms of our technology, this is where we're at. So we're kind of stuck again. You know, WFIRST is going to help us a little bit fill in this gap. We're not sure if it's going to be able to get to Earth sensitivity. There's that gap there. And so we're kind of back to this place where the Greeks were 2,500 years ago. We think that they're there. We think that there are Earths there. We don't quite have the technology to find them. But this time we have a plan. So it's not going to take us 2,500 years to get from knowing about them to finding them. This time we have a really exciting plan. So this is NASA's roadmap of exoplanet missions. So here's Hubble still operating. Spitzer, they ghosted it out. It actually got decommissioned in January, which was very sad. It was one of the 4 great observatories. So Kepler, unfortunately, stopped working in 2015. TESS is flying right now. As I said, it launched in 2018. It's just in 2 months' time going to finish its prime mission of 2 years, and then it's going to observe. The spacecraft is fine and the orbit is fine, so it's just going to keep observing for as long as NASA will give us money to fly it. James Webb, I haven't really talked about because it's going to do more characterization of known exoplanets as compared to discovery of planets. It's going to launch in the next year or two. That's a big 6.5 meter infrared telescope that you've probably heard a lot about because it's been very delayed and very over budget. WFIRST we spoke a little bit about. And so I wanted to just touch on these. So NASA has some really, really big ideas for what exoplanet hunting spacecraft might look like in 20 years' time. Basically, we want so that those direct imaging data that I showed you, we want to do that from space. We might have to use a star shade to do it. So that's where you have, you know, a spacecraft over here and 10,000 kilometers away, you basically have a star-shaped spacecraft flying in space that just blocks the light from the star. so that you can see the planets. So instead of that really cool instrumentation that blocks the light of the star being in your telescope, you're flying it, your formation flying multiple spacecraft, and that's 10,000 kilometers away. That's why I said this is like our big ideas that we're basically trying to build right now. Okay. So this is what we're currently at. This is where we'd like to be. So these spacecraft that we're trying to build, we're trying to plan and develop the technology for, we want to get from this, which is like, you know, in this image, Earth would be way in here and Venus would be way in here, and even Jupiter would be like, you know, somewhere out here. These are really far out planets. We want to push this in as far as we can. So with one of these telescope concepts that we've been discussing, we would be able to see things like Jupiter and Earth and maybe even Venus. And then that's super exciting because I said that's light from those planets coming to us. So we can just slap a spectrograph on that and start looking for molecules and atoms and biosignatures. This is where we want to go. This is where NASA wants to be in 20, 30 years' time. So this time we have a plan, which is super exciting. It's not going to take us 2,500 years. We think we'll be there in 25 years. So that's where I think, yeah, that's basically what I wanted to leave you with. And I'd love to hear your questions. Thank you so much again for having me. I'm sorry, Aurora, I meant to ask throughout if there were questions, but I hope you would have interrupted me if there were.
Yes, actually, we've had quite a few questions come in, and it's absolutely no problem. First of all, thank you so much. That was amazing, and thank you for your willingness to like break it down into such easy to understand steps. That was really what came across for me. I wanted to, we have a whole bunch of questions that have come in. So if you do have questions, you can go ahead and type them in the chat box. That's easiest. If you'd like to use the email or text, you can do that. Okay, let me see here. Brian had one way back here. Let me see if I can find it. One of the questions was, Brian, go ahead and resubmit that one because it got lost in the long list here. Linnea wanted to know if we're not, do you want to show your face instead of your screen?
Should I stop sharing?
Yeah. There we go.
Okay.
Okay, so Linnea is asking, I just lost it. Wait, give me a second. What if we're not side on to the star? Could we not tell if the planets are orbiting it? Okay, you get what I'm asking.
Yes, no, and that's a great question. So part of the reason that Kepler had to look at 200,000 stars is because most planets won't transit their star. It's actually a very small probability that you'll be lined up just right. So Earth, for instance, has like a 0.5%. So a 1 in 200 chance of orbiting this, of transiting the sun. If you're an alien civilization looking at our sun, you've got less than 1% chance of seeing Earth transit. So it's a very inefficient method because it misses most of the planets, which is why TESS and Kepler have to just look at so many stars to try and find the ones that are lined up. So if they're not lined up just right, there's still some options. So the radial velocity technique that I mentioned at the start, which just measures the velocity of the star, if the planet's not exactly edge on, if it's like up here, it will still pull on the star a little bit, like it'll be pulling on the star like this. So we'll see a little bit we'll see some component of it come towards us and then go back and forth. If it's totally pole on, like if the planet's going around like this and the star's moving like this, then from here we won't see any motion along the line of sight. So we won't see it then. But if it's side on, then that's where something like direct imaging, if it's far enough away and the star is bright enough, then you can use direct imaging. And then microlensing, again, that's just, if you have a very far away star that just happens to chance a line, you can see it with microlensing. So we do have other ways of detecting planets if they're not edge on. But yeah, transits is basically the cheapest one because you can go outside with a 10-centimeter telescope and measure a transit.
Awesome, thank you. Okay, that was great. Okay, so we have another question. How is it possibly raining glass? Can you explain that more?
Sure. Yeah, I love HD1897333 so much. So we have a bunch of different ways we can measure the atmospheres of these planets. If they're big enough and around bright enough stars, one of the things we can do is called transmission spectroscopy. So the planet goes in front of the star, so it transits, right? Now we know what transits are. The planet transits the star. So some of the starlight goes through the atmosphere of the planet. Most of the atmosphere will be transparent and the light will go through. But the atmosphere will have molecules in it, and those molecules absorb light at certain wavelengths. I mean, so like if you're in a room that has a window and a wall right now, So the window is letting light through and the wall is not letting light through. So molecules in the atmosphere act like that. There are windows in the atmosphere and there are walls in the atmosphere. So what that means is if you measure the size of the planet, it's a function of wavelength, so in different colors of light. Sometimes it'll look big because that's where the atmosphere is acting like a wall and blocking the light. And sometimes it'll look smaller because that's when the atmosphere is like a window and letting the light through. So that's how you can tell if something's got water or carbon dioxide, because carbon dioxide will absorb all of the 1.1 micron light. So it'll look like a wall there. So that's what we did with HD 189733. We did transmission spectroscopy, and we can see that there's lots of silicates in the atmosphere. We can also measure the temperature of the atmosphere because we know how close it is to like one of the hottest things. So we know it's thousands of degrees, and we know what happens to silica when you heat it up to thousands of degrees. One of the cool things you can see is like if lightning strikes a beach, it melts the sand, and you get these cool like glass sculptures basically out of lightning struck sand. So we know that it's melted glass because it's heated up so much. It's silicates that are heated up so much. We also know that once it gets basically like rain in our atmosphere, once it condenses to a big enough blob, gravity will start winning against any current or air that's pushing it up, and it'll start raining. The other thing we know from transmission spectroscopy is basically the wind speed at the terminator of the planet, so the edge between day and night on the planet. When a planet's transiting, we're always looking at its night side because we're seeing the back of the planet. The front of the planet's facing the star. So we're seeing the terminator. We can measure the wind speed. And the wind on HD 189733 is moving at like 2 kilometers a second. It's wild. I mean, these have the wildest weather in the galaxy, these planets. So we know there's silicates, we know the temperature, and we know how fast it's moving. So we know it's raining liquid glass sideways all the time, just from the pieces of information that we have. There's another planet, WASP 76, where we know it's raining iron, liquid iron. Wild.
Wow, that's amazing. That's awesome. Okay, we have some more questions. This is actually some questions from some kids who I think they're scouts, but I'm not positive. They could be Girl Scouts, Boy Scouts, or some kind of scouts. I'm just not sure what kind. But they are really interested in pursuing astronomy as a career and wanted to know, now that you're at this end, what do you recommend? What's the most important things you found that would be useful for them?
Oh, yeah, that's a good question. So in high school, I actually wanted to be a fighter pilot. I didn't want to be a scientist.
Wow.
But my eyesight's too bad. You can't tell. I'm wearing contacts. I'm wearing corrective lenses. But I always liked science in high school because it was very objective. Like, you know, F equals MA. There was an answer. I always got frustrated. I was a very type A student. I was a very teacher's pet. Like, I always wanted to get the right answer. And things like English and history always frustrated me because, you know, it was very difficult to know exactly what words the teacher wanted in what order to get an A on that essay. And that bothered me. So I always liked science because you could get it right and you knew you got it right. And there it was. And then, of course, you know, when I became a research scientist, I realized that enjoying science because you always got the right answer is the worst reason to enjoy science because you never, ever get the right answer ever again. The whole point of research is you don't know what you're doing. You don't know if it's the right answer. You have to keep researching. You're trying to find information that no one has found before. There's no way to check, like, this is it. I did it right. It's like, no, I think I found a thing. I've tested it every way. I think I found it. This is awesome. But I did like science a lot. When I went to university, I did physics and maths. I have a double major in physics and maths. The university that I went to didn't actually offer astronomy, and it wasn't until third year that I discovered astronomy and was interested in it as a career. I had actually been an amateur astronomer in high school. My high school's astronomy club was called the Zubenelga Newbies, which I'm sure some of you recognize that name. So yeah, I liked astronomy and I liked science and I did physics and maths, and then I realized I didn't actually really like physics and maths, but I really liked astronomy. And then I did a PhD, so that's a research project, and I really liked it. And then I stayed. Interestingly enough, a lot of people, when they become astronomy grad students and they want to stay in research, they become faculty, they become professors of astronomy. And one thing I realized I didn't want to do was become a professor of astronomy. Wasn't really interested in teaching classes. I wasn't really interested in like the whole university academia structure. And, you know, that gave me real heartburn. I was like, wait, what do I do if I want to do research in astronomy and I don't want to be a professor? And then I had a colleague at NASA who was like, hey, we have this job with Kepler. And I was like, wait, I could work at NASA? That's so cool. So then I took the job at NASA and got out of the university situation that I was in, and have been with NASA ever since. And so I really like it.
Wonderful. So one of the questions that came in is they wanted to know what other telescopes. Did you mention that the Hubble was doing work on, were there any others besides Hubble as well?
Sure. So I would say at this point, almost every big telescope on the planet or in the sky has been used for exoplanet science in some way. So we used Spitzer a lot to do transits and transmission spectroscopy. We used Hubble a lot and still use Hubble a lot to do transmission spectroscopy. We will use James Webb. There's a lot of the big, so like the Keck telescopes in Hawaii, these are the big 10-meter telescopes on the top of Mauna Kea. They do a lot of the radial velocity measurements of stars to find the planets. I'm doing exactly what you told me not to do and making fast motions with my hands in front of my fake background.
It's okay. The background's been pretty well behaved, except for the umbrella that keeps popping out of your left arm.
It's actually a circus tent.
Yep, there it is.
It's my kids' circus tent. So the big telescopes on the ground are mostly doing direct imaging or radial velocity. There's a lot of little telescopes on the ground that are doing transits because, as I said, you can find transits with a 4-inch telescope. We have a huge network of amateur astronomers that work on TESS data. So TESS goes and finds a star that has a periodic dip around it, and then we need people on the ground with their telescopes to go and follow them up. So if any of you guys listening tonight are amateur astronomers with telescopes that are, have auto guiding and a CCD on the back, you can absolutely help us find planets. Just get in touch and I'll point you at the right person. I would almost any telescope can do something planet related at this point.
Awesome. Thank you. Were you up for a couple of more questions?
Yeah, for sure.
Oh, okay, great. So one person was asking what ghosting is.
Oh, on my exoplanet roadmap.
Yeah.
They just turned it transparent as a way to say that it wasn't operating anymore, and that kind of made me sad because it made it seem like the telescope was dead. It was very interesting. So we had to decommission it in January, and when you decommission an asset in space, you really have to cripple it so that like no other nations on Earth could just like send it a message and be like, "Hey, Spitzer, we want you to work for us." So it was really interesting psychologically, like all of these engineers who've spent decades keeping the spacecraft alive now have to kill it. So it was really, it was a real moment for the engineers that I work with.
Awesome. Well, wonderful. Well, I think I've got one last question here that we can take. Okay, so this question is, maybe we'll take this other one because it's a good one too. Okay, so this question is, do we know of any objects from other solar systems, maybe including comets, that have traveled into our own solar system?
Oh, sure. Yeah. So there have been 2 really famous examples recently of this. So there's Oumuamua, which is some... it's a really interesting, like cigar-shaped rock that we found. Unfortunately, Oumuamua we didn't find until it was on its way out of the solar system. So it's kind of a rock that has traveled from somewhere, just happened to intercept our solar system. The sun gave it a bit of a swing around, and then we found it on its way back out again. So unfortunately, we didn't get to study it too much. All we knew is that it was kind of a bit redder than we expected for a rock and more elongated than we expected. And then we have another one that was just found last year, Borisov. So Oumuamua and Borisov. Borisov we actually caught on the way in, which is exciting. So that one we've been able to study in a lot more detail because it's just, we've got a lot more time before it's on its way out again. And it seems pretty ordinary. It just kind of looks like one of our asteroids in terms of like its shape and its color and stuff. And so it's really interesting. So, we found 2 in just only a few years, basically once we were able to scan the sky very quickly, very often. And so that kind of begs the question, like, how many times has this happened before? And how commonly does this happen? And how many times have we sent asteroids to other solar systems? So these are all really interesting questions that we get to ask now. And just the survey thing reminds me, if I can get on my soapbox for a bit, astronomers have gotten really good at observing big patches of the sky very quickly every night, looking for changes. So this is important for things like planetary defense, like looking for asteroids that are coming from nearby, or anything that's like changing in the sky, like some stars that are flashing or radio signals that are flashing. So this means that things like Starlink, which is this mega constellation of satellites that SpaceX is launching, are really detrimental to ground-based astronomy, because there's just going to be all of these satellites overhead all the time, which is, moving points of light in the sky, which is exactly what we're trying to find. So we're going to just get spoofed like thousands of times every night by these, near Earth satellites. So that's kind of frustrating, but SpaceX is working with the astronomy community now to see if there's ways to mitigate, the impact that this is going to have.
Yeah, that's very true. We actually had Dr. Pamela Gay give a presentation, and that was a lot of what she had talked about as well.
Okay.
So yes, thank you. Awesome. Okay. And well, I have just one last question that has, yeah, you got a lot of people agreeing with you right now. Grr, grr, grr. Okay, and one last question that's come in, which I think it's a pair of high schoolers. They could be graduate students, but they said they were students of astronomy. They want to know what do they do now? They want to help support the work that you're doing and other astronomers, but they don't know how to get started. Do you want me to put up a website of Planet Hunters, or do you? Okay.
Yeah. So there's two options. So planethunters.org is a citizen science project. Anybody with an internet connection and a computer can do it, or on your phone even, although it's a little screen. Basically, if you have some time, go and log in and start looking at the data. There's also a new one called Planet Patrol, Exoplanet Patrol, it's in beta mode. We just rolled it out like 2 weeks ago. So that's Exoplanet Patrol. That one's also using test data, but that one we need help basically working out which star has the signal on it. So Planet Hunters is you're just going to be looking at data, looking for dips, and showing us where there are dips. Exoplanet Patrol is going to be like images of the field of view, and you're going to try and help us work out where the star is that's making the signal. The problem with TESS is to look at that much sky at once. It's pixels. It's like individual bits of information are huge and often have multiple stars in them. So that's just, if you've got no other technology and you have no equipment, you can go do citizen science at planethunters.org or exoplanetpatrol.org. If you have a telescope and you're interested in contributing research, like, these are great student projects, like spend a semester following up a candidate, help us nail down the timing of when it transits, help us nail down how deep it is, what star it's on, how long the transit takes. This is all information that is much better from the ground once we've identified the signal from space. So there's many ways you can contribute there. And in that case, if you want to join this, as I said, we have this big amateur astronomy collaboration. I would say you could contact me, or you could contact Karen Collins. So Karen Collins is the head of that team. And if you just Googled Karen Collins TESS, you would find her.
Can you spell her last name for me?
Collins. Collins. Yes, Karen Collins. Sorry, my accent might be murdering it a bit.
Okay, I've got your volume turned way down so it doesn't echo over my speakers. So, okay.
Yes, once or twice I got excited and I heard myself.
Awesome. Well, thank you so much. We have so appreciated your time and your knowledge, your expertise, and inspiring other people. We've actually had people chime in from all over the planet. We've had
that's exciting.
Yes, people from the UK, as well as the Philippines, as well as there was quite a few people from New York, as well as California, as well as our own local little group. So we want to say thank you so much. If there's a way for people to get in touch with you, how would they do that?
You can find me on Twitter at Aussie Astronomer, or you can email me, jessiec@caltech.edu.
Great. You had that on your title slide, didn't you?
I think I had the Twitter handle. Would you like a copy of the slides for the club?
Yes, that would be great. Here, pop it up right now, and then I'll share it.
Sure. Let me grab it back. I'm still at the end. All right. Can you see? What can you see? Yep. Okay, so there's if you can find me on Twitter, or you can email me. And here, look, I'll just type it so you can see it. Oh, okay. Let me fix that. All right, can you see the title slide? Okay, let me stop and start again. Sorry, guys. Okay. All right, now can you see the title slide? Okay.
Yes.
All right, so there's my Twitter handle and there's my email, jessiec@caltech.edu.
Well, thank you, Jessie, so much for joining us tonight. We really appreciate having you here. And I know I speak on behalf of the club. Thank you so much for your time and your passion. You can clearly tell you're really excited about astronomy, and we love to see that. And it's very inspiring to everyone, especially kids, but also and really anyone who would like to learn more about the night sky. So
Right. I'm so lucky. I mean, I get paid to look for planets. I won the lottery.
I know you did. There's already a couple of people that want to get graduate degrees in lava based on
Absolutely. Make lava in a lab. That's incredible.
I know. How cool is that? All right. Well, thank you so much, Jessie. Everyone else, stay here just for a minute. I just want to extend a special thank you for you. So thank you, Jessie. And so wasn't she amazing? So if you'd like to right now, go ahead and type in a thank you to her. I'm going to send the comments straight to her as well. So if you'd like to tell her anything in the comment section, go ahead and do that now. If you want to be specific about something you especially liked, that would be really great. And that way she can actually read that for herself. One of her requests tonight was we wanted to reach more than just like one little club. And I told her no problem. So you can include where you're from as well with your comment if you'd like. Okay, so I'll give you a few minutes to do that. There were a few questions that came in, wanted to know what the name of our club was. It's Central Coast Astronomy or Central Coast Astronomical Society. My name is Aurora Lipper. I'm the current president of the society. You can find out more about us at centralcoastastronomy.org. Our website looks like this. It's really easy to get to. And even if you're not in the local area, that's totally fine. We love sharing our passion about the starry skies with you. And we have free talks like this every month. We also have free stargazing every month. And we are doing it virtually, obviously. And it's just one of the things that we like to do for the community. So you don't have to be in California. You don't even have to be in the United States. You just have to have a passion for looking at the night sky. I did get a few specific questions I was going to answer about binoculars. A couple of people asked, what kind of binoculars do you recommend? I have two recommendations for you. There's a cheap pair for about $40 from Celestron, which is really, really good. Let me show you a quick slide of it. They actually, I've just bought a pair and I was surprised how good they were for $40. And so the other, really, you can, any binoculars are going to be great. On our website, on Central Coast Astronomy, is a guide for how you can tell if your binoculars are good. And, you know, things are lined up and not looking all weird. So it's the Celestron Cometron 7 by 50s. You don't want to go bigger than a 10 by 50 because it's just too big. So here's a picture of those binoculars. You can get about $40. Actually, only $34. Not that expensive. The other ones that I really like are Orion's Ultra Views. These are more expensive from Orion. They're about 140. Okay, and these are, I've had mine for about 15 years. I love them. They're fantastic. But everybody has their preference. So I would recommend either one of those. You don't need those, but that's a great way to get started in astronomy. Okay, so you guys go ahead and put in your comments, put in your thank yous to Dr. Jessie Christiansen. She was just actually in the middle of dinner with her kids, and she says, oh, so she was so excited to share this presentation with us. So I'm really excited that she was able to do that. So our next presentation will be posted on our website when probably in about the next week or two, and you'll see it up here on the top, as well as all of the next events that'll be in here, including the virtual stargazing. There's also going to be a link in here that show you how you can post your own photos. So if you've been taking astronomy pictures, astrophotography images, or even doing videos, you can actually post those to our Facebook page, and we will have instructions for how to do that. All right, everyone, we're going to go ahead and sign off. I hope everyone's got their comments in so we can go ahead and do that. Thank you so much. Oh, thanks, James. Thanks, Jim. And I see Joe Richards, thank you, is here, and David Cryer and John Cherry. Excellent. Oh, all my friends are here. I didn't even look at the comments till like now, who actually has written them. So I'm so excited you guys are here. So If you do have any specific questions or special requests of things you'd like to see Central Coast Astronomy do this summer, just shoot me an email, aurora@centralcoastastronomy.org. I'd love to hear your ideas for ways that we can keep this astronomy thing going. I don't know if you know this, it's kind of a secret, but a lot of different astronomy clubs have been watching us to see how we do it so they can do it in their local area. So that's kind of cool. So anyway, I would love to hear ideas. If you've got an idea of how we can continue to do astronomy virtually online, sort of like this, let me know. I would love to hear what you've got to say. Okay, so thank you everyone, and I will see you at our next event. Have a great night.